Hello everyone. So today I wanted to quickly talk about Einstein's summation notation. And before I do, first I want to show you what an object like a vector or a tensor or like a matrix looks in a summation. So previously we talked about a rotation matrix and we wrote it as this. If we take the rotation matrix A and multiply it by vector V, we will get um, a vector v prime, which is just rotated by some angle theta. Now, if we want to represent this not in this notation, but in another notation, we can write it as this. We can write it as v I prime is equal to a I j v j, and all of that is being summed from j is equal to 1 to 3. Now, what does this mean? So, first I'll explain that to you. So, what is aij? What does that even mean? Actually, let's start with even simpler. What is vj? So, vj is just the jth component of the vector v. So, if I say vj, where j is equal to 1, that is the first component of the v vector. So if my v vector right here, if I say that my v vector is 1, 3, 8, 1 in the x direction, 3 in the y, and 8 in the z, vj, where j is equal to 1, vj is equal to 1 is going to be equal to 1. Vj is equal to 2 is going to be equal to 3. Vj is equal to 3 is going to be equal to 8. So j just describes which component. Now for a matrix where you actually have two I and j, it basically tells you the column and the row instead of just the column, right? So if we have a matrix A, which I can simply write down, let's say I have a 2 by 2 matrix. I have 1, 8, 2, 7, right? So if I have this matrix here, I have two columns, then I have two rows, right? So the columns, the rows here can be represented by the first index, which is I, and then the columns can be represented by the second index, which is j. So if I say what is a I is equal to 1, j is equal to 1, well, that's just the first number. If I say j is equal to 2, but I is equal to 1, then I move to this number. So hopefully that kind of makes sense. Now, when we multiply matrices with a vector, like in this case, this is the rotation matrix, what we're essentially doing is showing you what the process looks like when you try to find the new vector from the old vector through matrix multiplication. Now let's move into Einstein's summation notation, which comes in very specifically usually in regards to physicists and their math that they need later on. So let's say I have one down here. Let's say I have an equation which is vi prime is equal to the summation from j is equal to 1 to 3 of aij vj. Now in this case, we want to write this in an Einstein summation notation, which just means we want to get rid of the sum. Now in this case, you can see that we're summing over j, but not I, right? So because at the end of the day, we want to leave this as a representation of a matrix a vector of index I. But that index could be anything. So technically, this is a vector representation like this, where we just write I at the bottom, but if we specify the I, then it becomes a specific point. But if we leave it as I, we say that, okay, this is still technically like a vector representation. So if we take a look at the summation, you can see that there is a J component in the A and there's a J component in the V. If the J component is repeating between two multiplied, let's say vectors, or a matrix and a vector, or a matrix and a matrix, we're summing over that component, right? So in this case, we don't really need this sum here to show you that it's summing over. We will just write something like Vi is equal to Aij Vj. And since the j here is repeating, we will say that this whole thing is being summed over j. Now, here where we have j goes from 1 to 3, how do we know where this goes from, right? How do we know what the j goes from where to where? Usually that doesn't matter unless we specify it. And in physics, usually we don't really specify much unless we have to do a very specific example. So in this case, we can just leave it like this. Let's do another example. Let's say I have the summation from j. So if I just write down j at the bottom, it means I'm just summing over j, but I'm not yet specifying where I start or end to. So if I have the summation of j of a first matrix Aij with another matrix Akj, that I can, let's say, call the Kronecker delta, and that would be equal to Ik. Now you can see here that the summation is not needed because we have written j twice, right? We wrote the j here and a j here, which means that if the index is repeating, that means we're summing over that index. So we can just as easily write it as Aij Akj is equal to delta Ik. And one other thing you can notice, which we will specify in later videos, is when we sum over that index j disappears, and the answer will have the index which remains. In this case, I and k remained, the j's disappeared.